In the previous class we were discussing about eye resistance measurement, because we have started how to make resistance measurement. In that connection we discussed about how to make eye resistance measurement, like 100 ohm, 100 meg ohm, 10 meg ohm resistance are there, then how to make measurement, that is what we were discussing. Now in that connection we were using ratio transformer bridge. So using ratio transformer, how to make eye resistance measurement. For eye resistance measurement. So basically we are use ratio transformer, that is the primary you energize with the AC source, then you have center tap transformer, with both sides we connect the resistance, and then we connect say basically AC voltmeter, and then connect this, and then this center tap, the variable tap is connected to ground. So this is high resistance under test. This is also high resistance, but it is a fixed standard resistance. So essentially the basic working is like this: if this is taken as 0, then if this is taken as V1 and if this is taken as V2, then this current that is coming here actually goes through this, and then this V1 and V2 are 180 degree out of phase. So V1 and V2 are 180 degree out of phase. So that makes this current and this current are opposite. So this current is flowing like this. So if we take this current is flowing like this, then this current is flowing like this. So essentially this current comes like this, and then this current comes like this. So we have two opposite currents actually in this. One is given by this. So this current is given by V1 by R measurement, say Rm, and this is Rs. So V1 by Rs is the Rm is the current flowing here in this arm, and then V2 by Rs is the current flowing in the opposite direction. So at balance both are equal. So the this current actually fixed resistance current is actually V2 by Rs. So at balance these two currents are equal, that is this current is equal to this current. So I can equate these two. So essentially it becomes V1 by Rm actually equal to V2 by Rs. So one can if I can vary the say if I have a provision to vary the center tap, the midpoint winding, then this voltage and this voltage will be varying, and V1 by V2 will give you Rm by Rs actually. So that will make V1 by V2 would be equal to Rm by Rs actually. So essentially one knows V1 and V2, we can find out the Rm, the unknown value, because Rs is known. Since Rs is known, if V1 and V2 ratio is known, that is V1 by V2 is known, then unknown resistance can be calculated. Now, that is how it is working, but then the question is why it is very popular and why it is especially good for measuring high resistance values. Now, the beauty of the bridge is that leakage resistances, because when you are dealing with high resistance there will be a leakage. For example, if I take the circuit again carefully, look at it, you have the resistance connected here or voltage source connected here, and then you have the two you have the center tap, and then we have the two resistance here connected, and then this point is grounded and the voltmeter is connected here. Now, it is possible that you will have a leakage of this resistance from this point to this point to ground. Similarly, there will be a leakage from this point ground to this point. Similarly, there will be a leakage from here to this point and the leakage from here to here. Now, these are the leakage, 4 leakage resistances that is possible, that is I will call R1, R2, R3, R4. So, basically R1, R2, R3, R4 are leakage resistances. In normal case R1, R2, R3, R4 all will affect the measurement. In this bridge, these leakage resistance will not play any role in balancing the bridge, and net result is that this leakage resistance has no effect on the resistance measurement. That is why this bridge is popular, and one can measure 100 megohm or even 1000 megohm using this bridge, because these resistors R1, R2, R3, R4 are not contributing for the balance. So, these resistances are not contributing for the balance. Are not contributing. Now, the question is why they are not contributing for the balance. So, now if you look at the circuit carefully, that the at balance, this point, say this point is, say take as ground point as G and this midpoint as M. Now, at balance voltage across GM is 0, because we are adjusting the center point and balancing the bridge to find the value of unknown resistance. So, this is unknown resistance Rm, and then this is the standard resistance Rs. So, we are balancing the center tap and finding out Rm and Rs. Now, at balance essentially M is at 0 potential, that is the same as 0, because there is no voltage across this. That makes R2 also across R2 also 0 volt. Across R4 also you get a 0 volt. That means no current is flowing through R4 and R2. That means these resistances are not contributing for bridge balance, that is the bridge balance is not affected by these resistance values. So, that means the balancing point is not affected by these resistance. Now, if you look at R1 and R3, now this is a transformer, and the impedance of this transformer is very low. If we take as a voltage source, the output impedance of the voltage source is this transformer is very low. So, if we take this leakage resistance R1 and R3, they are merely loading the transformers. These currents are not actually flowing through this. So, this they are merely loading the transformer secondaries. Since the impedance of this the voltage source impedance, equivalent voltage source impedance of the transformer is very low, and the current actually flowing through this is creating no effect on the voltage at this point, because the impedance is very low. So, whatever current that is flowing, it is delivered by the winding, and that has no effect at the voltage at this point and at this point. So, essentially voltage at this point, say A and B, are unaffected by the resistance R1 and R3. That means the balance is not going to get affected by R1 R3. So, essentially all these 4 resistors R1, R2, R3, R4 are not contributing in any way balance in the balance of the bridge. The net result is you will get the resistance value Rm accurately. That is why this resistance can be even 100 megohm or 200 megohm. You will get accurate result, which is not possible in other circuits. So, this is a calibrated circuit originally used for capacitance measurement. This can be used for resistance measurement. So, these effectively these resistors are not contributing for the balance of the bridge. Why? Because if you look at it, this resistance R2, R4, see why voltage across R3 comma R4 is equal to 0 at balance. So, no current is flowing through R3 comma R4 at balance. So, it is not affecting the bridge balance. Similarly, if you look at R1 and R2, R1 and R3. So, this is R2 and R4, voltage across R2 and R4 equals 0 at balance. So, R2 so no current is flowing through R2 and R4. Similarly, if you take R1 and R3, R1 comma R3 are just loading the secondaries, loading the secondary of the transformer. But the output impedance of the output impedance of the transformer is very low. So, this loading is not affecting the low. So, the loading of R2 comma R4, I think loading of R1 comma R3, loading of R1 comma R3, loading of R1 comma R3 will not change V1 comma V2. So, the secondary voltage are not getting affected by the loading. So, no effect on the balance of the bridge. So, because of this, since this leakage resistance has no effect on balancing of the bridge, this method of measurement is very accurate. That is why it is a very popular circuit and it is extensively used for high resistance measurement, and it was originally developed for capacitance measurement. We will discuss about this later, how the capacitance measurement can be done using this bridge accurately. Now, only problem with this is that how to balance the bridge, because if it has to work well, then somebody have to manually balance this, then only it is possible to find what is the ratio of V1 and V2. Essentially means that you have to balance this and measure the voltage V1 here and V2 here. V1 by V2 will give you Rm by Rs. but then of course one can manually balance, and then one have to measure this voltage and this voltage. Now let us see how this measurement of voltage can be easily avoided by modifying the transformer slightly, so that one need not worry about measuring this voltage, because once you start measuring, then the error in V1 V2 will get in, and that will make the bridge not accurate. So how to avoid making the measurements? So essentially now if you look at the measurement, so V1 by V2, so V1 by V2 that comes as Rm by Rs. How to avoid measuring V1 and V2? That is other way around. If V1 and V2 are measured, if V1 and V2 are measured using a meter, then these errors, the error involved in this measurement, also to be considered, So the measurement of V1 V2 can be avoided by modifying the transformer. So the measurement of, so next is how to avoid the measurement of V1 and V2. How to avoid V1 V2 measurement. This can be achieved by modifying the bridge. That is, what can be done is that we can modify the ratio transformer slightly. What is done is you keep the primary of the transformer same, you energize this with the AC source, low frequency AC source, then wind the first primary, assume we have 10 turns here, that is you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, we have 1, 2, 3, 4, 5. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 turns. So, we have turns from this is 0 turns, and this is the 10th turn. So, 10 turns I put, that means whatever voltage I had given here, assume that this is also having 10 turns. Assume I have put 1 volt here, and this is 10 turn, and I also have 10 turns here, but at each turn I have taken one tap. So, I have taken this. So, that means this voltage across this will be 1 volt. If I given 1 volt here, then total voltage across 10 turns will be 1 volt. Then each one will be 0.1 volt. Each turn will have 0.1 volt. So, 0.1 volt, 0.2 volt, and so on. Each turn will representing 0.1 volt. So, if we write it, that is voltage, that there are 10 turns in the secondary one, 10 turns in the primary as well as in the secondary. In the primary and secondary. So, for 1 volt primary, then voltage across each turn of secondary is equal to 0.1 volt. So, each turn will have 0.1 volt across each turn of the secondary you will have 0.1 volt. Now, what we can do is that we can use center tap which is actually movable from one point to another. So, we can select here this sender tap can take, if it is making contact, if this movable tap makes contact here, then you will get 0.1 volt. If it makes it here at this point, then you will get 0 volt. So, 0, 0.1, 0.2, 0.3, and then when it makes contact here, you will get 1 volt. So, voltage across this, whatever you are getting, voltage across this depends on to which terminal it is making contact. Now, to make it more accurate, what is done is you add one more 10 here. What you do is, normally what is done is you take this, you wind just 110, this is 110. So, voltage across this also will be 0.1 volt. Now, this can be taken, and then this can be connected to this. So, what another 1010 is on, you wind one more 1010s here. So, you have 1010s. So, 3, 4, 5, 6, 7, 8, 9 and 10. So, you can have 10 tens, and this 10 tens can be connected to energize this 0.1 volt. So, now the we have this one more secondary winding, that is we have one secondary winding, we call this one as S1, this is S1, and this is another secondary winding S2. So, S1 is having totally 10 tens, and voltage across this each one is 0.1 volt, and there is another secondary added to this, this is only 110. So, voltage across this also 0.1 volt. So, that is applied to this to the second secondary S2, and the total voltage across this is 0.1 volt, and you have a 10 step 10 turns in this, that means voltage across each one will be 0.01 volt, because total voltage is 0.1 volt and divided by 10, that gives you 0.01 volt. So, voltage across this is 0.01 volt, and what is done is that this point is connected to this, the center point is connected to this, and this has its own secondary point, center tap. Okay. Now, if I take this point and this point, if I look at the voltage across this. So, if this is, for example, if it is at the midpoint 0.5, then the voltage at this point is 0.5 volt, because it is at the midpoint, this is 0, this is fifth winding. So, that means voltage at this point is 0.5, and then this is 0.5, and if this is sitting at fifth winding, then assume that this is also at fifth, then this voltage is 0.05, where each one is 0.01. So, it is at the fifth terminal. So, voltage across this comes to be 0.05, that means if I take this as 0, then this is sitting at 0.5, this is 0.05. So, that means this will be 0.55 volt. Voltage at this point becomes 0.55 with respect to this point. Now, for example, I can now I can move this. Suppose if I keep it at 0.4th terminal, then I will get 0.45. If this is at 5 and if this is 4, then I get 0.45. If it is, this one at first one 0.1, and if this is at fifth one, then I will get 0.15 volt. Like this, I can if I want, I can even add one more winding to get it more accurate. All that I need to do is that I add one more, for this I put one more 110. So, voltage across this, voltage this is actually 10 tens are there, and voltage across the full 1010 is 0.1 volt. So, voltage across this become 0.01 volt. So, that is 0.01 volt what you get across this, because this is 10 tenths, this is 10 tenths here and there are only 110 here. So, voltage across this will be 1/10 of this. Since this is 0.1 volt and you get 0.01 volt, if you want to add one more, I can energize this. Same thing I can do this, I can connect this to this, connect to this. So, you can use this one as a third winding S3. So, in S3 you also have 10 tenths, and the only thing is each one is 1 millivolt, each one is 1 millivolt. So, for example, if it is at midpoint it will be 0.5 and this at midpoint will be another 0.05. So, it will be 0.55, and if it is also at midpoint you will get 0.555 volt with respect to this point. So, by this arrangement, by varying this by varying the tapping, one can vary the voltage accurately, and there is no need to measure the voltage using a voltmeter to avoid the measurement error. So, if you look at this, this is a commercial ratio transformer made, and then this is how the commercial ratio transformer is made. This is a 3 decade ratio transformer, and one can connect the, for example, in this case if you want to connect the resistance, one can connect from the top and bottom. So, I will put it in order now. So, to measure this, so what is done is that for 3 decades, for 3 digit or for 3 digit accuracy, use 3 secondaries in the ratio transformer. First one, that is first one, first transformer, first secondary voltage is 1 volt. This is because you have 1 volt in the primary and then you have 10 tenths, that is S1. First secondary voltage is 1 volt, the step size here is 0.1 volt, step size is 0.1 volt. So, each turn is having 0.1 volt. Then another 1.1 volt winding is added, step size is 0.1 volt. The auxiliary winding is having 0.1 volt. This 0.1 volt energizes the second winding. So, what is done is that this 0.1 volt what we have from the first coil. So, first coil is here and the primary is here. This energizes the second coil. So, this is S2, this is S1. So, this is 0.1 volt. So, voltage across S2 is 0.1 volt. Step size, there are 10 turns here, step size in S2 is 0.01 volt. Step size in this thing is 0.0. Step size in S2 is 0.01 volt. Then this S2 also is having its own auxiliary winding. So, the here the voltage is 0.01 volt. The auxiliary winding of S2 is having voltage of 1 millivolt, sorry 10 millivolt. This winding of 10 millivolt is connected to the third winding S3, connected to the third winding S3. So, essentially if you look at this, we got a three windings. So, we start from our primary, then we had first S1 and it has its own auxiliary winding, then this energizes this S2. So, that is S1 and then S2, then S2 has its own auxiliary winding which energizes S3. So, this is 10 millivolt, this is 100 millivolt, because this is having only, this is 10 tenths and this is having only 110. So, 1/10 of this voltage is coming here. So, 100 millivolt is across this. So, you will get 10 millivolt, and now this is each one, there are 10 tenths. So, each one is having 1 millivolt. So, S3. So, voltage across S3, step size in S3 is step size of S3 is equal to 1 millivolt. So, now we can connect the entire transformer together, that actually looks like this. So, that means if I can use the sender tab, this can be connected to this and this will be coming as output, then and this has its own secondary tap that can be connected to this, and the final one is coming like this. Now, for example, for I resistance measurement, one standard resistance is connected here and then the other resistance is actually taken from here and then connected to this and then connect the measuring meter here, voltmeter rather. The voltmeter is connected at this point. So, this is standard resistance, this is resistance under measurement. By this ratio transfer method, one can measure the unknown resistance accurately without need to have any voltage measurement. Even this need not be accurate, because we are only making a null method, that is this one we are looking for a 0 here. So, the accuracy of this meter makes no contribution for the error, that is the resistance can be measured accurately even if this meter is not accurate, because we are looking at only the 0 point. So, and then this is supposed to be grounded, otherwise the leakage resistance what we have discussed, R1 and R2, R3, R4, they are all here, the leakage resistance are here. So, they have no effect on the measurement. Now, that I will remove this to avoid the confusion. Now, for example, if I keep this one at 0.5, the midpoint is at 5, and if this is at 5 and this is at 5, then if I take if I look at this voltage across this will be 0.5, 0.55, 0.5, there is a voltage at this point will be 0.555. Then if I look at the voltage at this point, that will be 0.5, because you have this is 0. If I take this as 0, this is midpoint 0.5, this is 1 volt. So you have voltage at this point coming as 0.5, this is coming as 1 volt. So essentially speaking, that if I take this as 0, this is 0 point. If I take this as 0 point, this is taken as 0 point. So this is taken as then automatically this becomes 0.5, because we know that this is at 1 volt, and if I take this as 0 point. So the question is, what is the voltage difference between this and this? Because our interest is, what is the voltage difference between this and this, what is the voltage difference between this and this. So this voltage is 0.55, and then with respect to this point, this is 1 volt. So with respect to this, it is 0.5 volt. That is with respect to this point 0.55, and if I take this one, this will be 0.45. So this will be 1 minus 0.55, that will be I will put it like this. So this will be 1 minus 0.555. That is because this is sitting at 0.5, this is 0.55, then automatically this becomes 0.45, and this is 0.05, and that makes 1 minus 0.555. So the voltage at this point is this much, voltage at this point is known, and then the ratio of this gives you the ratio of these two resistances. The ratio of these two voltages gives you the ratio of these two resistances. Ratio of these two voltages nothing but the contact points what is used in the ratio transformer. So since we are only worried about at what turns, each one is only at turns, and there are integral number of turns. So there is no question of any measurement error here, and the reading will be so accurate. Suppose even if the voltage changes, suppose if we are given here 1 volt, and if this voltage changes, then all the voltages are equally changing, the proportionally this voltage and this voltage proportionally changing, and this voltage also will be proportionally changing, and that has no effect on the balance of the bridge. So even if the excitation voltage changes, that has no effect on the balance. So the excitation voltage change voltage, that is voltage applied to the primary voltage applied to the primary changes then also the measurement is accurate. This is because the primary voltage change in the primary affects proportionally all the secondaries. So the ratio V1 by V2 is not changing. So there is no, because of this there is no measurement error even if the excitation voltage changes, and the voltmeter used to balance also has no effect. the second one is the voltmeter used, the voltmeter used for balancing is balancing will not affect the measurement, even if it is not calibrated, even if it is not calibrated. This is because it is a null method. This is because it is a null method. So, one can measure the resistance accurately, and then the leakage resistance has no effect, that we already discussed. So, the leakage resistance has no effect, and the voltmeter what we are using here for balancing, even if it has error, that will not produce any error in measurement, and even if the excitation voltage changes, that also has no effect on the measurement. So, this method is very accurate. One can go parts per million level of accuracy in resistance measurement, particularly high resistance measurement. Of course, this bridge can be used for medium level resistance. For example, 1K, 10K level of resistance, if I want to compare, I can compare and get it accurately. But if the resistance is too low, for example, if it is 1 ohm, 10 ohm like that value to be measured, this method is not suitable, because in that case there will be large current flowing here, and that will drop a voltage drop across the winding of this resistance, and then large current flowing here will also make you to consider the wire inductance involved in this. They will create a error. So, this method is not suitable for very low resistance. This method is suitable for high resistance measurement and medium level resistance measurement. So, one had to be careful in using this bridge. So, essentially this method of measurement method is good for high resistance measurement. Say probably greater than 10K, up to several hundred megohms. This is not good for low resistance measurement. Not good for low resistance measurement because low resistance because the current drawn from the transformer secondary, the current drawn from the transformer secondary will produce voltage error. So, this is not good for low resistance measurement. Of course, the main disadvantage with this method is that one have to manually balance this. The major disadvantage with this method is manual balancing is required. Of course, the electronic version of this also can be done without needing to balance the bridge manually. So, that we can do by simulating the ratio transformer electronically. So, all that needed is we have to produce, if we carefully look at it, look at the ratio transformer. All that required is that we have to produce two voltages V1 and V2 accurate. So, if we go to our original transformer and see, all that required is we have to have two voltages here, that is V1 and this is V2, you know, this voltage and this voltage V1 V2 to be generated. They are only degree out of phase, and then I should be able to vary V1 and V2 such that the balancing is done. So, that we can achieve using an operation amplifier. For example, I can show you how to make this measurement, this using operation amplifier. The same bridge can be obtained, but there no need to have the balancing. So, what can be done is that we can have a voltage source, AC voltage source. From oscillator we can obtain a AC voltage source. Then this voltage can be applied to the operational amplifier, so that I can put a follower and get the voltage. Since the output of the op amp is impedance of the output of the output impedance of the op amp is very low. So, this qualifies, you know, like transformer output, this gives you low voltage low impedance source, that is the output impedance is low, and then to get 180 degree out of phase I can give this one to another op amp, and there I can invert it. So, I put equal resistance here. So, I get this voltage and this voltage equal and opposite 180 out of phase, like the two secondaries of the transformer. Now, if I want to make ratio transformer bridge using this, then I will connect similar to that the two resistance, one is that Rm, another is that Rs, then connect this is the standard resistance Rs, then I put the voltmeter here and connect this one to ground. This actually we are now simulated artificially the ratio transformer bridge, because our aim is we want to avoid the manual balancing, because the ratio transformer has many advantages, that is you know, it is insensitive for the leakage resistances, and then the voltmeter error is not coming into picture, and even if this voltage changes, the measurement is accurate, it has no effect on the measurement. So, we want to take the goodness of the ratio transformer bridge and then remove its main drawback, that is one have to manually adjust, that is the main drawback of the ratio transformer, which we want to remove. So, that is what we are trying to do in this. So, we have done this. Now, what we do is, now we have to balance the bridge, that is if the voltage across this should be 0. If it is not 0, then one have to vary this and this. Now, that we can achieve easily by taking this voltage. For example, I can do one thing, I can take this voltage, and if I know that this is a voltage, then I merely amplify this. I just amplify this voltage, then I can connect this one to add this voltage with this. For example, if this voltage is not 0, say it is not balanced, that will happen if these two resistance ratio and these two voltages, okay, I will put it as V1 and V2, this is V1 and V2. If V1 V2 ratio is not same as Rm by Rs ratio, then the bridge will not be balanced. Assume that this is plus, this voltage is plus, then this plus voltage will be amplified, and then it will be subtracted. Assume that I put here R. So, this voltage whatever is there, if it is plus, then it will make this voltage more minus, that it will make the V2 increase. Again we are inverting and giving. So, it is equivalent telling V2 is increasing and V2 is minus. So, the it will output will come down. So, as long as the gain is higher here, the gain of this is higher, then the bridge is whatever small voltage is there, that will make this voltage higher and then balance the bridge. Of course, still you have a problem of making V1 and V2 measurement, which was not there in the case of ratio transformer, because if I put it like this and if I have a large gain, the bridge will be automatically balanced. One need not go and balance it, because if the error is plus, then automatically it puts more minus. In case if the error is minus, then automatically it puts it reduces this voltage. Of course, this voltage remains same, and that makes the bridge to balance automatically. So, how close it get balanced depends upon how much gain that we had given in this. Higher the gain and more accurately it will be balanced. All that one need to do is that I have to measure V1 and V2 now with the voltmeter, or I can convert V1 and V2 into DC and make accurate measurements. In that case it will give correct reading, but there is no way that we can avoid voltage measurement similar to what we had done in the ratio transformer bridge. So, essentially this bridge automatically balances. So, if you look at it, this the gain, say I will call this amplifier A, if the gain of the amplifier A is high, then bridge will get balanced automatically. Because bridge manual balancing is a problem, and this automatic balancing that way helps us. So, need not balance the bridge. So, bridge balancing taking place automatically. This is achieved by varying V1 and V2. This is achieved, this is because V2 is changing. It is changing opposite in opposite way, to the error voltage. That is this is considered as error voltage. This considers error voltage. So, if the error voltage is more, V2 decreases. If this is decreases, this increases. So, this error voltage, we call this as error voltage at this point. So, error voltage changes the V2 in opposite way, that is why the bridge is balancing. So, the error voltage opposite way to the error voltage. So, V1 and V2 ratio is adjusted automatically to balance the bridge. So, automatic balancing is achieved, and V1 and V2 ratio get automatically adjusted. Then one can find V1 by V2 will be equal to Rm by Rs. But V1 V2 have to be measured, but V1 and V2 must be measured. Which was not there in the case of ratio transformer. The error induced by V1 V2 will be added to the measurement error. So, the error in error in the measurement of V1 and V2 affects the resistance measurement. So, it is not as accurate as the ratio transformer bits. So, it is not as accurate as ratio transformer bits. In addition to this, it has another drawback, that is the main drawback. If the op amps introduce phase shift error, then measurement will not be accurate. That means we have to see that the phase shift produced by the op amps are very small. So, for this to work, make sure the phase shift produced by the op amp, the phase shift introduced by the op amp should be very small. Op amps must be very small. This can be achieved by setting a wide bandwidth op amp. So, it is required. So, high bandwidth op amps required. Stages required. Op amp stage is required. Alternatively, use op amp with low gain, use several op amps, each one is with low gain from each stage, So, we will be discussing about this little later, how to reduce the phase shift produced by the op amp. One way is that if the frequency of the measurement is low, this is not a serious problem. So, if one uses low frequency measurement, for low frequency measurement, this is not a serious problem. Frequency measurement, say few hertz, then phase shift is not a problem. Phase shift is not a problem. So, one can use the op amp for automatic balancing, and of course, you will have to measure V1, V2 to make the measurement accurate, and keep the frequency of the measurement low, so that the error is small. So, this is how the high resistance measurement can be made, which is not susceptible for leakage resistance and so on. And this method is very popular and is extensively used as a ratio transformer technique. Next class you will see the other issues of the bridge method.